I think we were looking at this slide, which was a time domain signal. And this could be something that you measure with a radio frequency antenna, doing an NMR experiment or an NMR image. So you elicit a signal from the patient, and your antenna picks up this signal, and it's voltage versus time. And we're looking in general here. We're going to look at the criteria for sampling this signal adequately. So the question is, how fast, how many samples per second do we have to acquire in order to sample this signal such that we have adequately sampled? And we looked at a specific example where we were sampling at a certain frequency, sampling frequency, and we compared what we obtained when we sampled at 1/8 that frequency. That means we basically skip 7 samples, take one of them, skip 7 samples, take one of them, compared to this one. Okay. And one way of looking at the outcome was to look at the Fourier transform of this signal. And so the Fourier transform is going to give us the representation of the sinusoidal oscillations in this signal at different frequencies. And here are the frequencies in hertz. This is a temporal sample. This is 150 milliseconds of data out to here. And then these are the relative amplitudes of the sine waves and cosines at different frequencies in hertz or cycles per second. So we're out here at 10 kilohertz. This is 2 kilohertz. Okay. So this happens to be sampling in the audio, right? This is where if you're a Wi-Fi or a high fidelity person and you like, stereos and stuff like that, you worry about fidelity across this frequency because this is what you can hear, right? Some people can actually hear right up to 20,000 hertz. When you're young, you can hear these really high frequency sounds. When I was a kid, I'm not sure if this is still true. If you go to a mall, and you walk by a jewelry store, does this still happen? You hear that really high frequency tone, and it has something to do with the alarm in the jewelry store, and you lose that in your 40s. After you start walking by jewelry stores, you don't hear it anymore. When you're a kid, you get this super high frequency. It's like up around 20 kilohertz. I don't know what it is, although you can Google it and find out. But so anyway, when we drop our sampling frequency here considerably, almost an order of magnitude, right, by a factor of 8, the waveform looks a little different, right, when you plot it. And when you take the Fourier transform of the fewer points and we plot it out to the same number of hertz, we see this periodic function. Okay, so something happened here, right? And it is basically, we can't uniquely identify all of these frequencies with this sampling rate, right? And this is called aliasing, is when high frequency data is sampled incorrectly, and it shows up as a low frequency data point in your data. But we'll take a look at that in more detail. Right now, the important thing to note is like there's a periodicity to this function, right? All of these points here are absolutely replicated here. Okay. We can look at an example of a frequency being encoded as the wrong frequency when you undersample, just by a trivial example here. So we have a sinusoid at a specific frequency and a lot of sample points on it. Okay, and then these sample points are enough to measure that frequency quite accurately, right? The frequency and the phase. If I drop, the number of sample points, say by a factor of 10, so I take every 10th point or something, I get this point, and then the function goes on happily, and it hits this value at this sample point. It keeps on going on, this sample point, this sample point, this sample And so I'm not sampling with high enough frequency to measure that higher frequency, those oscillations. But what it looks like when I've asked, well, what sinusoid is that I've sampled, it comes out as a lower frequency. It looks like I've sampled power in the signal at a lower frequency. And this is the concept of aliasing. Okay, so that's misrepresentation of high frequency power in your signal, and it looks like it's a lower frequency. And there's a MATLAB demo that we can do where you can play with this concept, like create sine waves in MATLAB, sample them at different frequencies, and see what the signal actually looks like, right? And does it look like a low frequency signal? Does it look like a high frequency signal? And where does that cutoff occur, right? How fast do I have to sample this in order to accurately find out what the power is of the signal at that frequency, right? Any guesses as to how many data points you would need across here, what rate you would want to sample this sine wave in order to make sure that you were able to adequately determine how much power is in your signal at that frequency? If you look at the curve, there's kind of a common sense answer, right? You know the answer?
2 times the.
Yeah, you've done this before. Yeah, that's good, of course. Yeah, so and what does that come out to? It says, well, like if I have a curve that looks like this, if I sampled, say, each one of these points on the peak, I sampled at that rate, it would just look like a straight line, right? So I would have missed that function entirely. Yeah? Oh, thanks. Oh, it's not up on my screen, so can I get to it? Oh, and the mouse isn't even up there. Okay. Sorry, we're going to take a short break. There's some kind of, did it go away? Awesome. But also the mouse never came back, right? That's a problem. So let's say, no, turn it into a laser. Huh. Oh, there it is. Okay. And tips and show. Now it's turned into a laser. Okay, that's good. All right, back to business. If I sample at a rate such that I'm uniformly sampling the peaks here, that will just look like a constant function. So I missed it, totally missed it, right? However, I sample this one, and then this one, and then this one, and then this one, at least I'll get one up, one down, one up, one down, one up, one down, and it will have the amplitude that's associated with that sine wave, right? So that gives you a sort of a visceral, best guess as to what the lowest frequency you want to sample is, right? And so that frequency would be a point at not one full cycle of this sine wave, but at a half cycle. So you need 2 points per cycle, right, in order to sample it correctly. And that's called the Nyquist theorem. And we'll look at that in a little detail. We were going to do this, but we're behind. So I'm just going to scooch through these. Okay. Oh, this reminds me, if you were unable to attend the Dr. Liu's review of the delta function and linear systems and stuff like that, I would watch the video online, okay, because it's a great additional explanation of a lot of these functions and how to work with delta functions, etc. We're going to use this function a lot, which is the comb function, which is a set of delta functions that are separated by some gap, okay? And we'll call this the sampling function of the comb function. It can be called an impulse train, right? And it is a continuous function in X. It's defined everywhere, so you can integrate as a function of X. It has, measure and everything like that, right? And it's defined such that there's a delta function at each unit of separation. You can scale it. You can create a comb function in 2 dimensions, right? Quite simply, just by having a 2-dimensional delta function in the argument and summing up all of these delta functions that are separated in delta x and delta y. And so we'll call this the sampling function. It has, it's a function of the continuous variables x and y, and the spikes are separated by delta x, delta y. And so this, to write it out as the comb function, we just have this scaling is here to essentially normalize for the numbers of spikes per unit area, right? Is what that normalization is doing. Okay. So we can use the comb function to start looking mathematically at what it means to sample a continuous function. So if I have this curve here and I multiply by the comb function here and essentially integrate across such that the delta functions, each individual delta function sifts out a value of my underlying continuous function, right? Then I get this sampled version of my continuous function. Remember, this sampled version is still, it's a continuous function of x, right? It's defined everywhere. It just happens to have the values of this continuous function at these individual points, at these x values, okay? But it's still defined everywhere. It isn't just a set of numbers, right? It is in fact a function of x. And so that's, in terms to do calculus and integration and things like that, we want a function of x. We don't just want a set of numbers, right? So here's our sampled continuous version of f of x. It's essentially the continuous function multiplied by the comb function. Basically, you can write the comb function out as this sum of individual delta functions that are separated by delta x, okay? And this can come inside as just the discrete values of the function f of x at those x locations, okay? This is a set of numbers, right? It's just coefficients. So you can just stick them in a matrix as a set of numbers, right? With commas between them. Okay. But this is the sampled version of the function. Okay. Same thing in 2 dimensions. Everything works in 3 dimensions for that matter, but you just make the delta function a 2D delta function, and now you have a set of numbers, but they're indexed with 2 indices, depending on where you are in the plane. Okay, we go back to our example where we had the comb function, and now we have a sampled version of the continuous function. And we're going to tell you what the Fourier transform of a comb function is, and we're not going to derive it. But interestingly enough, the Fourier transform of a comb function is a comb function, right? And if I have a comb function in the variable x, when I take its Fourier transform, I get a comb function in kx, or spatial frequency, right? And that's an interesting phenomenon, right? That a set of spikes, when you take its Fourier transform, you ask, well, what are the frequency components in that set of spikes? You go into the Fourier domain, and it's a set of spikes. So it's a set of individual or discrete sinusoids or cosines added up to give you like this set of spikes, right? And it's not obvious actually to me that would be the case, right? But when you look at it, when you think about it, you say, okay, well, if I was to create a function, with a set of spikes, or if I'm going to integrate sine waves multiplied by a set of spikes, right, in the Fourier transform and ask, well, which values are going to give me non-zero values for that integral? You would anticipate it would be the cosines and the sines that align up with your original set of spikes, right? So if I have a cosine and I'm doing my Fourier integral and I have a cosine going up and down like that, and there's a spike at the max of each one of those wave peaks, then that integral would come out as a number. If I shift the frequency slightly of the cosine with respect to the set of spikes, and I integrate out to infinity, right, that's going to be a smaller number, right? And so when you take it to its example at infinity, you can imagine that the only values in that Fourier transform that are going to give you coefficients back are going to be these discrete frequencies that have sort of a 2 pi, 6 pi, 8 pi phase shift between the spikes, right? So you always hit the peaks. So you're going to get a kind of a set of sinusoids as opposed to some continuous function. So it's not, in some ways it's intuitive, but anyway, so the Fourier transform of a comb function is a comb function. Interestingly, if you're separated by delta x in the spatial domain with your comb function, say we sample, once every centimeter or whatever, when I go to the spatial frequency Fourier transform of that comb function, the separation in frequency unit is 1 over delta x. That's what the separation between the spikes are, okay? So here's our original comb function separated by delta x. Take its Fourier transform, I get another comb function separated by 1 over delta x. Okay. So as these come closer and closer together, these spikes in the Fourier domain move farther and farther apart. Okay. These are going to represent our sampling, right? So if we have a function and we're going to sample with this comb function, right? That's, as I get close, delta x gets smaller and smaller and smaller, that's like a higher spatial frequency sample, right? I can detect things at much higher spatial frequency. And that, as we'll see, has something to do with how far apart these spikes become, right? So now we have the Fourier transform of our sampled function is what we're going to look at here. And recall, we're going to multiply our continuous function, gx, by the comb function, right, in order to generate our sampled function. Okay, so the sampled function is defined everywhere at every x, right? It's not just a list of numbers, but it only has values at those locations where the comb function has a spike. Okay, everywhere else it's 0. We can still take the Fourier transform of this thing, and so this is going to be the Fourier transform of the sampled function, the continuous sampled function. By the convolution theorem, which we talked about when we talked about the Fourier transform of a product, which is the continuous function and the comb function, are the two functions that are in this product, we can convolve the Fourier transform of the continuous gx, so without any sampling considerations, right? This is the absolute continuous Fourier transform of this function, that's right here, convolved with the Fourier transform of the comb function. So the Fourier transform of the comb function we just discussed is a comb function in the frequency space, right? So now I have the continuous version of the Fourier transform of my continuous function convolved with this new comb function here. And the new comb function has spikes at spatial frequency values, or k values, separated by 1 over delta x. Okay, so that's what this algebra says here. Okay. I can take this continuous function And this convolution is it's the convolution over the sum of all these spikes, right? By linearity, I can just bring this inside here and say, well, I'll just convolve each spike and take the sum of those results as my final function, right? So when you do that, this sifts out, this convolution sifts out this value, right, of g, right? So I have a function that is continuous in k, this g value here. It's essentially the Fourier transform is continuous in k, but after this step, I have to add up multiple copies of that Fourier transform, of that continuous Fourier transform, in order to get the value at a specific point, kx, right? And that value is what this continuous function is at replicants of the function. I just displace, each time n goes up, I displace by 1 over x, right, which is the repeating value of those spikes. So I have essentially the first value when n is 0, and then I have the value of gkx plus this displacement, and then plus twice that displacement, and plus 3 times that displacement. So inside, my original zone that I'm looking at this function, I have all of these additional sums of that function at these higher frequencies. Right? And so when you look at a picture of what that looks like, here's our function. It's a continuous function g of kx, right? We have sampled it, and so we take its Fourier transform, and what we get under those conditions is that function, okay, here, plus all of these replicants of that function. So at any one value here, you have this function plus what this one is at that displacement, right? Yeah.
Can you explain once more why g of x is continuous? Aren't we sampling it at some frequency?
That's a great question, and this is one of the things that is like an aha realization, is the reason we're looking at g of kx as a continuous function is that, recall that this sampled version of our original continuous function is itself a continuous function, right? So all of this stuff we're looking at now is all defined for every x value and defined for every kx value or spatial frequency, right? And it's not, we haven't done a discrete Fourier transform or anything here. This can all be done with continuous x values. Okay, we'll see that, like, there are ways to look at all of this stuff as discrete Fourier transforms and discrete analysis, right? But when we take this Fourier transform, it is of an absolutely continuous function, right? It's defined at all x. It's not just a set of numbers that we're doing a discrete Fourier transform on.
When we do it in real life,
Yes.
is that discrete or is that still, like, for example, maybe is that still discrete, or is that still, or is that continuous, or is that converted to discrete?
That's a very good question. And so the question is, when we start to do this in real life and we look at taking this Fourier transform, for example, or these things, is it going to be something that's discrete? And absolutely yes, it will be something that's discrete. And that comes with other issues, right? But in order to understand what it means for this continuous function to have aliasing, it doesn't have to be a discrete thing, right? It does have to be sampled at a specific rate, right? And it's obviously very related to a discrete function because so many of the values in this continuous function are 0. There's just these peaks here, but it's a subtle point, but it's It's worth noting. I'm glad you asked the question. So this function here is a continuous. So this is a continuous function, okay? And then basically it's, you know, when you look out into higher and higher values of kx, these are all continuous values. They're all defined everywhere. And what happens is the function itself becomes periodic, right? It's a continuous periodic function. And inside, you know, those, so here's our period. This is 1 over delta x here. The function will just repeat itself with that frequency. And inside this zone here, there, to get from here to here, you sum up how all of these outside functions actually add up to every point. So, so if we sample fast enough, let me see. If our original function that we sampled, this guy here, right? If we sample with high enough frequency to sample all of the spatial frequencies that are in that function, right, then it will be what's called band limited. The values of the spatial frequencies will roll off to actually be 0 beyond some high frequency level. So you can imagine I have some function that's relatively smooth and that it has sort of maximum spatial frequencies in it, right? And so if that is true, if it's, that's called a band limited function, then the frequencies that are used to compose that function roll off to 0 at some value kx equals capital U. Okay, so it's called a band limited function. There are some very easy examples of band limited functions, right? So if I have a plane wave, a sine wave in the plane, right, then sampling beyond that sine wave, right, if I go far enough, it doesn't matter, right? So that's sort of, that's the only frequency that's there, right? If I sample some function that is a composite of sine waves, right, and then you stop adding sine waves that are at higher frequencies to make this Fourier composition, then beyond those frequencies, there's nothing there, right? So it's a band limited function. We don't know that ahead of time. What oftentimes when we're sampling something like the X-ray image or X-ray shadow, you know, what are the spatial frequencies? There's no reason why that should be band limited, right? In the sense that differences in X-ray fluence as a function of position can be all the way down to, you know, molecular levels, right? Same with MR. If you have more and more time to acquire data with more and more averaging, you can essentially go down to a very small spatial limit. And that's usually limited by the amount that molecules of water will randomly diffuse within the time you're making your picture, right? So if you make your picture over, you take your data over 10 milliseconds, the water will bump around and that'll smooth out. So there is some kind of band limiting there, but it's a very high frequency. Yeah. Oh, well, I just gave an example of when, say, the highest spatial frequency you have is some sine wave. That's the limit of the frequencies that are in your signal. Yeah.
It's not something you determine. It's just something that comes from the function that you're sampling.
True. I mean, you know, whatever that function is, if the function is random noise on if you're measuring, say, with an antenna, and you put that antenna up next to a patient and you measure voltage as a function of time, you can go up to, you know, gigahertz and there'll still be noise there, right? So that does not have a cutoff frequency or a band limit. The noise is just, it'll go on forever, right? It's an interesting aside. It's like, what is the band limit of the noise? And how do you get rid of that noise that's at higher frequencies? You just filter it out. You don't want that noise. Just filter it out of your signal. Okay. So you can, in fact, if you have a signal and all of your information is in some band and you don't care about the high frequencies, it is often wise to filter the signal so that those high frequencies are known to be gone, right? So we'll just filter at some width and then we're good. That's often done in MR. So this is the band limit of our signal. And if the band limit is such that, we're at this point, our sampling comb is such that it puts the replicants of our function at 2 times this band limit, then these functions just don't overlap. So when I ask what is the value of my Fourier transform at this point, I don't have to worry about leakage of signal from one of these replicants here because I know it's gone, right? And so making these separate is the goal of sampling such that you don't get aliasing. So I need to sample at a high enough frequency such that if I know what my band limit is, my replicants of this Fourier transform are separated. Okay. So to avoid aliasing, 1 over delta x, that is my sampling rate, has to be greater than 2u. So it has to be greater than this width. Okay. Okay. And so this is called the Nyquist criterion. Very famous. So if it's not satisfied, then this spacing between replicants starts collapsing in, getting closer, and you start getting actual corruption of your data at these frequencies, right? Where this overlap occurs, and that's called aliasing. Exactly the same thing happens in 2 dimensions. So if I have, a bandwidth of my signal here, and I sample at a rate such that the replicants of the 2-dimensional Fourier coefficients of this function are far enough apart such they don't overlap, then I am adequately sampled. If I can't afford to sample at that rate for whatever reason, and I sample at a lower rate, then these things start closing in, and inside my field, I will get combinations of this original and the replicants. Right? Okay, well, we already did this. Let's look at, this is a visceral sort of example of the change of what the function actually looks like after you sample it as you change the sampling frequency. So let's say we have a sine wave here and we have its frequency, it's 1. So it's 1 cycle per, let's call these centimeters just to make it real. So 0 to 5 centimeters, I get 1 cycle every centimeter. Okay, so it's just a sine wave here. If my sampling delta x, in this case dx, or delta x is 0.1, right? So between each sample point, I have 0.1 centimeters. That means I sampled 10 times per centimeter, right? I get a very nice representation of that sine wave, right? If I cut my number of samples in half, so now delta x is 0.2, so I'm only sampling 5 times per centimeter, it's still adequate, and I still see something that looks quite like the sine wave. Looks pretty good. If I cut my sampling rate such that now it's 0.3 centimeters between each point, or 3 millimeters between each point, and plot those values, this original function now looks like this. It's starting to look a little distorted, but it's still sampled okay. Here it is at 0.4. This is what it looks like. And at 0.5. So what does this point mean? It means I'm sampling every half centimeter, I'm taking a sample. So I get 1 up, 1 down, 1 up, 1 down. So now I have a sine wave, but it's literally a point up, a point down, a point up, a point down, a point up, a point down. And this is the Nyquist point right here. After you go beyond this and you start sampling at lower frequencies, interesting things start happening to your function. It starts looking like a much lower frequency function, right? And in fact, here we're getting one big sort of cycle of a sine wave, or fraction of a cycle of a sine wave, right? So these are all corrupted through aliasing. Well, we just did this example. So if your period here, well, we're calling these millimeters, I guess, period is 1 millimeter here, then you need a sampling rate such that the distance between points is half of that. Okay, so 2 samples per spatial period. So let's suppose, and we just discussed this also, here's our detector, right? And we put it up behind the patient and we shine X-rays through the patient. And now we have high spatial frequencies. But the detector, right, doesn't have the ability, or the digitization has the ability only to sample at a certain rate, right? It's sort of a fixed rate. What we can do is we can filter our signal such that higher spatial frequencies before they hit the detector get filtered out. And that way we know that inside our sampling scheme, we don't have this aliasing because the signal that hit the detector has already been filtered. And a way to filter, for example, a really bad way to filter, but a potential way to filter is just, you know, if you want your spatial frequencies to be represented by a rectangle function, so you know you've got spatial frequencies inside a certain frequency bandwidth and nothing outside, you can convolve your function with this sinc function, right? And that's equivalent in the opposite Fourier domain to multiplying by this rect function. This is flipped around in space and frequency, but this is where that duality is helpful, right? Just like if I'm working in this space and I want to see that my spectrum is band limited, I convolve with this function, right? Okay, so that's spatial frequencies. And okay, so now we're going to go to CT scanning, an introduction to CT. Okay. So I'm sorry, we've kind of a little bit behind schedule, but okay. Good. So here's a basic CT scan, how it's set up. It's a cylinder, and we'll see an MR scanner is also a cylinder. Lots of scanners are cylinders. And you put the patient inside the inner gap in the cylinder, and basically we'll shine X-rays through the patient. They'll hit a detector. We'll take that shadow image, and we'll take it at many different angles. The great thing about CT is that the patient can show up with lots of hardware, oxygen bottles, ECG leads, clips stopping bleeding, all this kind of stuff. And you can just put them in the scanner and scan them. Okay? In MR, as we'll see, Dr. Liu will show you probably some videos of this. And anytime you do, if you join a lab, this is an MR lab, you have to do a safety course, which is don't bring metal near the magnet because it has a very large magnetic field, right? So it makes life more complicated. But in CT, what you have to worry about is the radiation that comes from this thing when you're, scanning. The table is controllable, so you can push the patient back and forth, take pictures of whatever part of the body you want. And in CT nowadays, it usually takes a few seconds to get all of your data. So the patient shows up, it takes them 5 minutes to get them set up on the table. They come back, take 5 minutes to type in all the characters to make the right scan. And then you hit go and it goes whoop, and it's done, right? The acquisition part is really, really short compared to the rest of the time. So it's really great. Here's some modern CT scans of a human brain. So you can see very nice details between, you know, the gray matter here and the white matter tracks. Here is contrast injected into a patient, and then you isolate the vascular structures in the brain because the contrast absorbs so many more x-rays in the surrounding brain. So you get beautiful, detailed angiograms, these are called. So oftentimes you're looking for like a bulge in one of these vessels that you need to go in and either surgically repair or put a coil or something in. You can scan a patient head to toe on a CT scanner in literally 2 seconds, right? So the table just goes, and you acquire data such that you can get it from here to there, right? And so you'll inject a contrast agent into the patient such that it lights up all the vascular structures that you're imaging as you pass the patient through. Some interesting things happen in CT, for instance, when patients have metallic implants. Metals obviously absorb a lot of x-rays compared to tissue. And so they have a very, very bright signal in the raw data. And they can often completely obscure the signal, say, between them. And you can imagine, you know, I can tell you what's here because I get enough angles this way, but for a point right in between, it's really obscured by the fact that all of the x-rays are starved out in these views, right? That signal is there, you just have to pull it out. You have to get rid of the signal from these things, right? With some kind of signal processing, and you can reconstruct the picture. But straight out of the box, it's pretty hard. CT is usually obtained in a 3D format all the time. It's not usually obtained in 2D anymore. It's just a 3D chunk. And then you look at the patient in a natural imaging plane subsequently. After you reconstruct the 3D data, you'll cut that data in different sort of morphological planes, whether it's the coronal or the axial or whatever. Here, this is a heart shown in an axial view. So these are planes where the patient's lying on the table, and if you just took a saw and cut them down the middle like that, then that's called an axial plane. Coronal is a plane that's parallel to the floor, and sagittal is the orthogonal to those two. So it would cut them right down the center of their body, right down this axis here. That's called a sagittal plane. So this is an axial plane through a heart. This is a coronal. So we're looking from the patient's chest down towards their back. Here we're looking from their left arm towards their right arm. And that's called a sagittal. And the data is, you know, it's discrete in that there is 0.4 millimeters between each estimate. Like each bright dot that makes this picture, the separation between those is 0.4 millimeters. So it's like 0.4 by 0.4 by 0.6 is the size of the voxel on CT. So you get a ton of these numbers, right? Each scan, if you look at the raw data and all of the images that are reconstructed, normally each scan, you can compress it down to about 2 or 3 gigabytes per data set, something like that. This is a volume reconstruction. And so what you do with the data now is you have these voxels that are bright and dark. And all we've done here is we adjust the opacity of a voxel depending on its brightness, and then render that object as if we were just looking at it with a camera, right? And the lighting model here is very, very simple. This is just 3D graphics, right? Where the brightness actually comes from the object itself. So it's not really any complex lighting and shading. You just like let the object glow at a certain brightness depending on the CT value. And you get these absolutely ridiculous representations of human anatomy, right? They're super gorgeous. And importantly, there are these vessels here. This is the right coronary artery running all the way down the back of the patient, and then it comes out the aorta there, et cetera. And so this data to obtain that entire volume was obtained in 160 milliseconds, right? That many voxels came out of that scanner in 160 milliseconds. So it's the data rate now is quite extraordinary. If you want to go back, normally radiologists, when they look at these data, they don't normally look at that volume. For whatever reason, they just don't. Sometimes they do if it's a complex case. Specifically, non-radiologists like surgeons will look at those 3D volumes to try and get an idea of what's going on. For instance, in a congenital heart, it's hard to know what you will find, what's connected to what, and so you make this 3D volume. Physicians, like radiologists, are used to looking at things in 2D planes, and so they'll reconstruct pictures in 2D planes. And so this is a left ventricle. This is the blood in the ventricle, the myocardium, and this is the right coronary artery in that patient. And what has happened here is a computer program ran down and found where the center of this artery was all the way down the artery, and then it cut away tissue above that so that we could look down into the middle of the artery, right? So it did a carve through that object, and then you look at it, and what you're looking for is any, morphological strangeness, like if that artery got really narrow and then got thick again. That narrowing is a classic sign of heart disease. And so this is the right coronary artery, and this is the left coronary artery going down here. Very small structures are illuminated quite well. If you take those data that are acquired in 160 milliseconds, and you take enough data for 1 second, like 1 heartbeat, and then we just reconstruct data at 160, and then 320, and then 480, and we just step along a heartbeat and play that data back. It looks like this, right? And so you create now what's essentially a movie of the beating heart, trivially, without any sort of fancy stuff, right? And the reason, again, that this is bright or illuminated is that you've injected a contrast agent into the blood of the patient. It absorbs the X-rays really well. It shows up as this very bright object. And then all you have to do is tell, renderer, oh, only illuminate objects above a certain value, and this comes out. Like, there's no smart segmentation or anything here. You just turn your level up, and then this pops out on screen. So it's very, very simple. So let's look at the basic structure of how the data is obtained for this. And essentially, in the original implementation, or the original sort of invention of CT, it was thought there'd be a source and a single detector, right? Because who would have thousands of detectors? That's so much data. So a single detector, and you would raster across the patient, and you would measure how many X-rays hit the detector as a function of position across the patient, right? And so that would give you one view through the patient, through their chest, out their back. And then you rotate the whole system, and you do that raster again at a different angle, right? And this is very simple, right? It gives you a one-dimensional function, which is the absorption of the X-rays as it passes through that associated pathway through the patient, right? And to be perfectly honest, when you reconstruct CT data, normally what you do with the data now is you put it back into a form such that it looks like this data, right? And then the reconstruction is mathematically simple. Right? However, this would take a long time, and it did take a long time. This was the original setup of a guy named Godfrey Hounsfield, who made the first CT scanner. And this was his detector, this was his source. the source actually was not an X-ray tube or X-ray light bulb. It was actually some radioactive material with a very small hole right here. So a beam of, high energy photons came out of that hole. And then he measured the intensity of the beam over here, right? And instead of moving the detector and the source, he just moved the sample, right? So he just rastered the sample through here and then rotated and then rastered the sample through and rotated and rastered the sample through. Okay? And in most modern X-ray imaging labs, that's how it's still done, is that you have an X-ray tube on this side, which is now a very sophisticated X-ray tube that you purchase from a manufacturer. You have a big panel over here, which is your detector, right? And you can just use anything. You can take the detector out of a mammography machine or whatever, and you put it here. And then you have some very nicely computer controlled way of rotating and translating your object. Most of the time, this is this cone of X-rays coming out, and then you just rotate it in that cone. So jumping ahead, we can say, well, if we want to speed up by, say, a factor of 5, we could have 5 things here, 5 detectors, and just raster across more quickly, right? These are called generations. You don't need to know these, though. And then if we make a cone, right, or this is called actually a fan beam of X-rays. So that fan beam covers the entire patient in one shot. So if I go poof, I get all of these pathways through the patient in one shot. I can have a row of detectors here and just pick up that data very quickly, right? I don't have to raster it across. The only thing I do is I rotate this whole system around the patient and get the views, right? And for many years, this is the way CT was done commercially, right? There were basically, well, before I go here, there were very many, connections here to these detectors, and that data had to go out onto a computer on usually some kind of ribbon cable of, that came off the scanner. And in order to get that data out, they would rotate the scanner and the ribbon cable would rotate with the gantry, right? And then you'd have to stop and rotate back the other way because you didn't want, if you kept going, the ribbon cable would just come off, right? And then Siemens actually pioneered a technology where they put brushes on a connecting ring, and all of the data went out over those brushes. And so they could rotate the gantry the same way all the time. And they could rotate it as fast as they wanted, right? Or as fast as mechanically you could rotate the thing. And so now gantries rotate really fast. Well, relatively fast. The next way of increasing the amount of data, now I have, say, 1,000 detectors here, and I shine X-rays here. And so I simultaneously get 1,000 points. I can also stack them, in the Z direction. So head to foot, I can stack a whole bunch of detectors that way and just keep doing that, right? And so finally you get to a case where now most scanners are about 1,000 detectors this way and somewhere between 64 to 320 this way, right? So you basically have a 2-dimensional picture that you're sampling for each position of the source and the detector, which is usually called the gantry. So here's a set of pictures showing the basic structure. Here's my X-ray source, makes a fan beam. I've got a detector and I'm going to rotate that thing continuously. Okay? And that'll give me all these different views through the patient. A spiral scan, what I do is I continuously rotate my source and my detector, and then I continuously move the patient through that beam from their feet to their head. And I'm collecting data continuously, but it's on a spiral trajectory, right, through that patient. So if I want to ask, well, what's happening at this slice of the patient? I don't have a lot of data exactly at that point. In fact, I only have one view at that value. I interpolate to get the other views, you know, at that Z location. You can also just move the patient, take a shot, move the patient, take a shot, move the patient, take a shot. Yeah.
In this scenario, are the patients like tied down so that they don't move when the
You don't need to tie them down because it's moving, the table moves relatively quickly, but not quickly enough that they would, you know, fall off or shoot off the end of the scanner or anything like that. So normally they're just comfortably lying there with pillows and things like that. The closest you get to tying down patients actually happens in MR, remarkably, and that's because you have to fasten coils onto their body, and you would like to get the coil as close as possible to what you're imaging. And so it does, let's say, test the limits of someone's claustrophobia when you have all of these coils and you like strap them down with Velcro. Right? They're like, I'm in this thing, and you say, oh, everything's gonna be fine. Just relax. And some people, no problem, they just fall asleep. Other people, when you put that strap on, it's not good. And in fact, when you do cardiac, you have their EKG, right? So you're watching their EKG and you strap them down, you go back to the control room, you look at their EKG and you go, oh, what? And their heart rate's at like 140. And say, are you okay? And they go, yeah, I'm fine. It's like, okay, we'll give you a Valium, then you come back, right? So anyway, in CT, the gantry is pretty short and wide. So you do get some claustrophobic reaction, but very, very rarely. Right? So this is a modern CT scanner. This is what we have over in the Thornton Hospital. And, you know, this video is working. That's kind of what it looks like. If you could see through the skins, it's really zooming. It rotates once or 360 degrees every 280 milliseconds. That's going to go down to 230 milliseconds soon. This is the detector array inside, and there's the X-ray tube there. And so ours is 256 detectors this way and about 1,000 detectors this way. Right? And that's what it looked like when they were putting it together. All of this hardware spins at that rate, right? So it's a pretty hefty load, right? And so when you look at, say, the power supply for the X-ray tube, and you ask, well, what's the G-force of this thing when it's up at its top rate, right? And it's like 9, something like that, right? So it's not something you can ignore. You have to put it together really well, and you don't want it to start shaking apart. The worst thing is when you start a CT scanner and you start to hear this weird noise, like, you're like, what the heck is that? You don't want to hear that, right? Everything should be fastened down. They all have their interesting noises, right? Here's some websites you should go, and every hospital, the engineers eventually take the skins off the thing and fire it up and watch, right? And so you can see this thing really spinning, and then there'll be stuff blowing around, and so they're having a great time. An interesting version of the CT scanner was proposed by Siemens for the last 10 years, where they said, you know, we have our X-ray tube and our detector. You know, if we got really efficient, we could put another X-ray tube and another detector at an angle. And so, you know, ideally, this is 2 scanners, right, sitting there 90 degrees apart. And so it essentially increases your temporal resolution, your ability to make a picture by a factor of 2, right? So it's a dual source scanner, it's called. And the other thing you can do is you can make one image at, say, 80 keV, like at a certain energy coming out of the X-ray tube, and they can turn the energy up on this X-ray tube such that there are higher energy X-rays coming out of here, and you can make a different picture. So you can get 2 pictures simultaneously or close to simultaneously. So that's called a dual source scanner. Let's what is this fast? Oh yeah, this is just that shows and that's kind of in real time. That's what it looks like when you scan a patient. It goes zoop, like that. That's a relatively slow table speed. So this is CT scanner usage over time. Okay, and the technology appeared commercially in the 80s, early 80s. It appeared in scientific labs in the 70s. And it was used pretty, I started doing MR research right here, right, in 84. And we thought, like, when I was a grad student and I got into an MR lab, I was like, oh yeah, but CT's cool, but it's done. What else are you gonna do, kind of thing. And it just continued to evolve. I mean, all of these imaging techniques continue to evolve. When you think they're finished and there's nothing more you could do, then somebody comes up with something new. And then over that time, Siemens introduced, sort of in the late 80s, this helical scanning where you had the brush contacts. So you could just rotate as fast as you wanted and do spiral scanning. And so the use of CT, because the images got so much better, ramped up, right? And this is like millions of exams done in the United States per year, right? And then when they started putting multiple slices together, so they made the first one was a scanner that had 4 slices, then 8, then 16, then 32. So the VCT, it's called, the GE scanner that had 64 slices, became the best-selling medical imaging piece of equipment ever, right? Because it was so useful, right? And you could, if you had one in your ER and somebody came in 30 seconds, you knew what was going on, right? You just like, whoop, do that, because you have this wide detector, zips through the patient really fast, and you see these great pictures. So you can see that usage just went through the roof, right? And nowadays it's like over 120 million scans a year, something like that. So interesting side note is that many scans, right? With everybody that goes to the hospital, if they get one of these scans, it becomes a source of background radiation in the population. So you're talking about numbers that are population numbers. And so the question is, like, what's the average high energy radiation absorbed by a human being per year? And when you run the numbers, most of it comes from radon in the ground. A lot of it comes from cosmic stuff. Just walking around in San Diego, every year you get 3 millisieverts of radiation, right? And when you look at the people that get CT scanned, they also get an extra anywhere from 3 to 10 millisieverts. So when these numbers start getting that big, you ask the question, well, is this a health concern now? Because so many people are getting irradiated. There's a lot of controversy in the use of calculations to determine whether or not it is a health concern for a population. As a project, if you wanted to look into that, the modern literature on CT radiation, it's a very interesting topic. It's also very politically charged, right? People have certain beliefs and go there. But it's a super hard thing to measure because you're trying to look at a very small delta in background radiation and measure a delta in cancer risk. Cancer risk is this huge number already. And so you're trying to measure a very small change on a number that's fairly high, right? And it's statistically a very hard thing to do, right? So, if somebody wants to look at that. Well, these are generations. This is in the book from the first generation that was that single detector rastering across all the way now to these, multi-detector, multi-row CT scans. People have classified them with these generations. You don't have to worry about it. This is where we are now. The next thing coming, and we won't talk about this though, is direct X-ray detection with photon counting detectors, right? That's what's going to happen next in CT. So I welcome you to go to these websites. They have these beautiful animations of them exploding scanners, such that you can see what's, the component is the makeup of the scanner. Here's, we looked at a detector here. Sitting above the detector, this thing, and we looked at this sort of on the problem set, is the anti-scatter grid for this imaging field, which, remember, it has a cone structure, right? And so you can see through it if you're on a direct line of sight, but then when you go to an angle, you can no longer see through this thing, right? And so that basically the X-rays that hit it would get absorbed by this anti-scatter grid. And so those X-rays that bounce off the patient and go at a random angle and will not give you any useful information about the shadow cast by that patient, they get absorbed by this, or the majority of them get absorbed by this. So what does the signal look like that we measure? Here's our source. The X-rays are going on these trajectories through the patient, and we'll simultaneously measure, say for a particular time interval, we'll integrate up the X-rays that hit each detector element, and then call that our counts, for that time. In a modern scanner, when this thing rotates around, it rotates again around, ours does it every 280 milliseconds. And you normally get about 1,000 views, okay, over that 280 milliseconds. And so just divide that 360 degrees, right, by 1,000 views. There's a slight angular motion there when you're integrating the photons that are occurring, and that gives you your temporal sampling. So it's 1,000 samples per 280 milliseconds. That kind of gives you your temporal sampling. And you ask the question, okay, what, if I look at X-ray intensity as a function of position along my detector, here's my position, right? And I just look at one view, so it's a very small temporal window, small angular window, and I look at the middle detector here, which is going through the patient's sternum, their heart, bit of their aorta, and right through their spine. Okay? The fact it's going through the spine means a lot of X-rays get absorbed. And so when I look at my X-ray intensity, it drops here. It gets quite low because we're going through the spine, right? For a X-ray beam that is going mostly through lung to here, then I get a lot of X-ray intensity at my detector because there wasn't much stopping the X-rays, okay? So you get this negative image, right? So this is going to show up as a high value on our CT scan, because remember, on the CT scan, we're going to actually have intensity on the image is the proportional amount of X-rays absorbed, right? That'll give us a bright thing. Whereas when I'm counting the X-rays on my detector, that means I get a low number of X-rays. If the patient is thick enough, and this happens, people get big. If they're really thick, you can have a case where when you go to measure the X-rays, you just don't see any. They're gone, right? And so that's a bad situation to be in because you don't have any detail there. So with a very large person, usually you crank up the energy of the X-rays, because remember, the higher energy we go, the less that, mu vector, and the more we'll get through the patient, right? For very slim people who are little skinny people, then you can drop the energy of the X-rays right down and you still get a good shadow, right? So there's a big difference in the number of X-rays get absorbed by a larger person than a smaller person. And so when the patient comes in their vitals, it's always on the chart is given their body mass index, and then you set your X-ray energy based on that. So when we change the orientation of the source and the detector, remember they rotate together, and we look now, if I look through here, here's the spine. It's now hitting this detector element, so it moves over to here, that minimum. And over here, our beam is actually missing the patient altogether here. So it gives you sort of the back, you know, as many x-rays as you're going to get. This is like I0, the intensity that came out of the tube is hitting your detector, right? Other than those that got absorbed by the anti-scatter grid. Okay. Here's a more sophisticated version of that Godfrey Hounsfield experiment, where this is the X-ray detector, this is the tube, right? These are pre-filters of the X-rays that are going to hit the object. Okay, so you can put things, if X-rays are coming out of here, remember we said, well, let's get rid of the really low energy X-rays. Simple way of doing that is put a little piece of copper there. All the low energy X-rays get absorbed, the higher ones come through. This also has, this is a really neat system in that it has a grid of these pre-filters so that you can modify basically the Fourier structure of the beam before it hits the patient, right? And so here, and then this is the phantom, and you just rotate this phantom, and that simulates the whole thing rotating around. So if you want to do X-ray imaging as your big deal, getting into a lab that has these bench setups is a good idea. They're really fun. CT speed. This is just essentially the samples per second or the number of pixels in an image. You know, back in the 70s down here, and this is a log scale, right? It's going up. It's just going up basically exactly, you know, with Moore's law is how it went up. There's just more detectors, more data, more stuff. And so the early images, you know, 2 images at 80 by 80 pixels took 20 minutes, right? Now, 320 images at 512 by 512 takes 280 milliseconds. So that's a significant increase in speed. Part of that has caused X-ray tube power design to become a big issue, because if you're imaging with that type of speed, you need a lot of X-rays in a short period of time. Just an X-ray flash, right? And so these are high power tubes that are used for this. And remember, the energy of the X-rays coming out of that tube, right, has a spectrum. And so we know when we set the voltage between the anode and the cathode at 120 kilovolts, the highest energy photons are 120 keV. We don't get that many of them. Most of them are down here at the sort of the mean value of this distribution, somewhere around 50 to 60 keV, right? And basically, as we turn down the voltage between the anode and the cathode, the spectrum changes. The fundamental parameter that we're interested in measuring is this mu value for a material. And remember what that is. If I have an intensity of X-rays coming in, I measure that coming out. The number that are absorbed, or the fractional loss of X-rays, is the intensity of the beam coming in with this mono-exponential decay, with this constant, right? And that's called the linear attenuation coefficient. Okay, so that's the most important parameter in X-ray imaging. And we looked at an example where we became comfortable with the fact that this is a simple mono-exponential decay with this linear attenuation coefficient. If you want to go back and look in the book, they have other ways of deriving that, or you can just say, oh, I believe this, that it is a simple exponential decay. So looking back, when we're looking at X-rays, I think we discussed this, right? Is that I will have an attenuation that is proportional to the mu value and the path that the X-rays are going on. So I have to integrate from entry into the object to whatever depth I'm at. I integrate that to get my total attenuation across that depth to this value X. And I have to look at the energy dependence, right? Because mu, in the perfect world, we would measure mu as a polyenergetic function. We know mu changes as a function of energy. And so we would do both of these intervals. We would do it over the energy spectrum of the beam, and we would derive mu values at different energies. You have to get a lot of data to do that. And normally you need to change the incident beam energy at least to do that, or measure different energies on the back end after they pass to the patient. And so most of the time we just say, you know what, we're going to figure out a mu that's at the mean energy value of that distribution. Yeah. Oh, it just means that mu is a function of both position through. So that's that's what we're going to integrate over here. But it's also a value of energy. So you could equally well put a comma here. I mean, it's just like, it's a 2D function. Okay, we are now at 12:20. So what we're going to do on Wednesday is we're going to look at mathematically how you set up this problem such that I have a function fxy. That function is actually going to be mu xy. Like, what is the linear attenuation coefficient as a function of position in the plane? And we're going to look at X-rays passing through that function and creating a projection image. And we'll collect a bunch of those projection images and make a picture. And so mathematically, we'll set that up on Wednesday. Okay.